Welcome back to the AI Blueprint. So for the last 6 episodes, we've optimized our agents, we've tuned our vector databases, and we built out our routing layers. But the ultimate way to optimize your AI infrastructure budget? Don't use an LLM at all. Today, drawing on some really brilliant insights from principal AI architect Parth B Joshi's Substack, we're mapping out the definitive framework for exactly when to pull the plug on generative tech altogether. Look, every vendor out there is structurally incentivizing you to use language models for literally everything. Today, we build the framework for when to say absolutely not. Okay, let's jump right into this. We're looking at a fundamental dichotomy here. On one hand, you've got the stochastic, probabilistic reality of a looping LLM graph. It's chaotic, it's unpredictable, and frankly, it is expensive. On the other hand, the clean, rock-solid execution of a deterministic 5-line Python script. You see, the question most engineering teams ask nowadays is, hey, can an LLM do this? And with today's frontier models, yeah, the answer is almost always yes. But that is entirely the wrong question. Capability isn't the bottleneck anymore. The real question you should be asking is, are you sacrificing clean, governed, deterministic logic for a probabilistic model that really had no business being there in the first place? And honestly, that leads us right into the classic hammer and nail trap. Think about it. Model vendors want you to use more models. Cloud platforms want your workloads spinning on their compute. The whole industry is practically screaming at you that an LLM is the magic bullet for your next problem. But falling for this, it has massive consequences. Every single task you route through an LLM that didn't actually need to go there comes with a heavy, compounding tax. You're burning inference spend, you're injecting totally unnecessary latency, you're risking weird, non-deterministic behavior, and you're expanding your governance surface area for no good reason. Let's put some real numbers on this. Think about the operational cost. 400. A standard LLM call introduces a massive bottleneck into your system, usually hovering right around 400 milliseconds just for the time to first token. In the world of high-performance back-end architecture, 400 milliseconds, that is literally an eternity. When you start multiplying that delay across thousands of requests a day, across dozens of different microservices, the accumulated lag is just staggering. Now, hold that 400 millisecond lag in your head and compare it to a classical algorithm. A standard regex pattern executes in what, roughly 2 milliseconds? 2. Put those side by side and you instantly see the latency squeeze at scale. Why on earth would you pay a 400 millisecond penalty plus the compute cost to do something a standard function handles basically instantaneously? Right. So this highlights a really uncomfortable truth about modern dev cycles. We often choose the LLM solution just because it was faster to prototype on a Tuesday afternoon, not because it was the right architectural choice for a system that actually needs to survive in production for the next 3 years. We absolutely have to move past this prototype bias. So how do we fix this? We break down our operational boundaries into 3 non-negotiable core no-go zones, starting with Zone 1, strict math and exact compliance. This first red flag zone is all about systems where absolute accuracy and exact data retrieval are non-negotiable. If the answer exists verbatim in a SQL database, wrapping that lookup in an LLM is practically begging for a hallucination. Using an LLM for zero-tolerance math, things like balancing a financial ledger or running statistical aggregations, is a structural failure mode from day one. Look, yes, language models can do arithmetic, and sure, they'll usually get it right. But they are also completely capable of being confidently and plausibly wrong, and catching those errors programmatically is a nightmare. For deterministic math, you need deterministic code, period. It's not just about saving a few bucks, it's a strict absolute correctness requirement. Moving right along, let's look at the second boundary, Zone 2, the latency squeeze and the high-frequency costs associated with it. In architecture, speed and volume dictate whether you survive or crash. When you scale to millions of high-frequency tasks, every single ounce of friction bloats your cloud bill. If you're using an LLM just for simple request routing, like deciding which queue a customer service ticket goes to based on a few known attributes, you are just bleeding inference compute. That routing logic should be a fast, simple decision tree. And honestly, if you're repeatedly hitting an LLM with the exact same inputs without a semantic hash in front of it, you're literally multiplying your latency and paying for the exact same probabilistic reasoning over and over again. High input repetition screams legacy caching, not LLMs. Okay, on to our third strict boundary, Zone 3, static data transformations. This is all about dealing with known data schemas. Whenever your source and target schemas are strictly known, you aren't doing AI. You're looking at a classic data engineering problem. Just look at how cleanly these tasks map to standard legacy alternatives. Transforming a JSON payload into a CSV? Put that in a standard ETL pipeline where it executes in microseconds. Doing rule-based classification with a fixed set of categories? Spin up a code rules engine. Checking for prohibited terms? Write some explicit validation logic. You do not want to encode strict, rigid rules inside fragile, unpredictable prompt structures. Legacy code is cheaper, it's exponentially faster, and most importantly, it's fully auditable. Right, so how do we actually stop the bleeding and fix this bloated architecture? We need a completely new framework. We have to rebuild our ingestion process using a deterministic first routing framework. I like to call this the pragmatic triage engine. This is the exact diagnostic discipline you need in place before your system generates even a single token. Let's map this out. When an incoming request hits your system, step one is routing it through a strict deterministic validation layer. We check it against our rules, our caches, our lookup tables. If it clears that, we move to step two, the semantic necessity check. We literally pause and ask the system, hey, does this payload actually need a generative model? And based on that answer, step three handles the routing perfectly, either sending it up to the optimized AI stack we built in earlier episodes or shunting it straight down to cheap, lightning-fast legacy compute. Now, that semantic necessity check, it really boils down to one absolutely vital question. Does this task require reasoning under genuine uncertainty? Basically, does it need judgment, synthesis, or the ability to interpret really ambiguous inputs? If the correct output can be fully specified ahead of time using rules, basic logic, or a lookup table, then the answer is a hard no. Throwing an LLM at it is just adding massive complexity without delivering a single ounce of actual value. So if there isn't any genuine uncertainty, that request shifts directly over to one of these legacy compute fallbacks. We're talking schema mapping functions, explicit validation logic, standard database search indexes, or just plain old hard-coded decision trees. By rigorously routing these well-defined tasks away from your LLMs, you are going to make your entire infrastructure drastically cheaper, remarkably faster, and, this is huge for enterprise environments, so much easier to govern. Which brings us to the core philosophy of this whole explainer. Great engineering isn't about using the newest, flashiest tool for every single job. It's about using the right tool for the job. The true mark of maturity for a senior engineer or an AI architect isn't figuring out how to shoehorn a frontier model into every single microservice. It's having the diagnostic discipline to know exactly when to say no to the vendor hype and when to fall back on the rock-solid foundations of deterministic code. Knowing when not to use a language model isn't some weakness in your AI strategy, it's actually the ultimate proof that you really have one. Next week, we'll be transitioning into optimizing context windows. But until then, if you want to keep building architectures that actually survive production, hit subscribe and make sure you read Parth B Joshi's full teardown on Substack. But I'll leave you with this final thought to chew on. If you were to audit your entire AI stack right now, today, using this deterministic framework, what percentage of your LLM calls wouldn't even survive the week?